Here we go. So hopefully this shouldn't be difficult for folks. If people have a pretty good handle on how to attack this kind of table.
Yeah.
Hopefully. Yeah, so just briefly, the thing to sort of remember about this is that this number refers to the total mass of the atom we're talking about. And we know that the mass comes from what? What two subatomic particles really account for most of the mass of an atom?
Protons and neutrons?
Right. Yeah, electrons do have mass, but very little, about 1/4000th, I think, of a proton or a neutron. So this would be the total mass. The fact that that's carbon should tell you something about the number of a particular subatomic particle. What does it tell you? How many protons, neutrons, or electrons it has?
Protons.
Yeah, it tells you how many protons it has, exactly, because the number of protons is the determinative thing about what element it is. The number of electrons tells you what charge it is, and the number of neutrons helps to determine what the mass is. And that's pretty much it for that one. Okay. So, empirical molecular formulas. People want to review how to do that. Or is this fairly easy for folks to do?
Personally, I don't mind going over that one.
Anybody else want to look at this quickly?
Yeah.
Sure.
Yeah.
Sure. All right. So what information are we going to use to determine how much phosphorus and how much oxygen is in this compound? Like basically, where do we start with this?
Would you divide 21.8 by 50?
That'll give us a percentage. That'll give us a percentage of phosphorus. Does that move us any closer to figuring out what? I guess we could do that. So 21.8 divided by 50. So that tells us we have 43.6% phosphorus. So the rest must be what?
Oxygen.
Rest has got to be oxygen, right? That makes sense. So oxygen has to be 56.4%. All right, so we've got this far. So what do we do next?
Do we find the moles?
Exactly. We need to find what the ratio of moles is between phosphorus and oxygen. So if we just assume we had 100 grams, then we have 43.6 grams of phosphorus, right? So how much does a mole of what's the mass of a mole of phosphorus? How would we find that out?
30.
How we find it out? Maybe the
P table.
The P table. Well, you're not going to be able to use the P table during the test, but you will be able to use this. So hopefully everyone has one of these. So you just look it up. So which number is it?
30.
So here's phosphorus. Here's phosphorus right here. So which number are we going to look at? Are we looking at 15 or 30.974?
30.974.
And what does that represent?
The molar mass.
Right, that's the mass of 1 mole in grams. So multiply that by 1 mole over 30.974 grams. Now I'm just going to change this to grams for both of them, because percent just means out of 100, right? So it means out of 100 grams. So how many moles of phosphorus do I have?
1.40. Do you keep going or do you round? You don't round, right?
Keep going.
Okay.
You can use as many significant digits as you want right here.
76322208.
That's probably 5 is probably enough. Then that just means more numbers you got to punch in. So that's how many moles of phosphorus we have. How many moles of oxygen do we have? What's the molar mass of oxygen?
15.999.
Right. Now, a really simple mistake that a lot of people make here is they think, what's the molar mass of oxygen? And they go, oh, oxygen is O2, that's 32 grams per mole. But we're not dealing with oxygen molecules here. We're dealing with oxygen atoms, because it's oxygen atoms that are in this compound, not oxygen molecules. So you only want the mass of 1 oxygen atom, because we want to know how many moles of oxygen atoms we have. So how many moles of oxygen atoms do we have?
3.5252.
3.5252 moles. So we got some weird numbers here. We can't have a compound with, like, you know, P 1.4, O 3.5. That's not going to make any sense. So how do we get around that?
Multiply by 2.
Is that the easiest way? Because if we multiply by 2, then I've got 2.8.
Oh, are we dividing the smallest one first?
There you go. Yeah, divide by the smallest one. Make the smallest one into 1 and then see what happens to the larger number.
Wait, quick question.
Yeah.
How do you know we're dealing with oxygen atoms? Like, what is a good way of knowing?
Oh, because it says we have a sample of a compound. So there's a compound. That means it's a group of different atoms. And it says it has phosphorus and oxygen in it. So that means it has phosphorus atoms in it, and it has oxygen atoms in it. An oxygen molecule is all by itself. An oxygen molecule is not bound to anybody else. It's just oxygen bound to oxygen. So that wouldn't be part of a compound, okay? This is a compound all by itself.
Uh-huh. That makes sense.
Yeah, good. So if we divide both sides by 1.4076, what numbers do we get?
1 and 2.5.
1 and 2.5. Okay, so we have P1, O, 2.5. Well, that 2.5 is not going to fly, right? So what's a whole number ratio between phosphorus and oxygen?
2 to 5.
Right, 2 to 5, because these both need to be whole numbers, because in a molecule I can have 2.5 atoms of oxygen. That's not going to work. So our final answer for A, anyway, is P2O5. So that is the answer to A. Now, what does empirical formula mean? What's the difference between empirical formula and molecular formula?
Empirical formula is reduced, and molecular formula is like not reduced.
Reduced in what way? You're right. I just don't know exactly. Reduced in what sense?
Like, that's the smallest whole number ratio.
Bingo, exactly. Yeah, I can't lower it any more than this. That is the simplest ratio of those two things. Doesn't mean it's the actual ratio, because the actual ratio might be much bigger, because the size of the molecule might be huge. There could be 200 phosphorus atoms and 500 oxygen atoms. So, I mean, that'd be a massive molecule. But the simplest ratio between 500 and 200 is 2 and 5. But the molecular formula tells us exactly how many atoms there are in each one. And the only information we have about the actual molecule, other than its ratio of phosphorus and oxygen, is its molar mass. And its molar mass is around 284 grams per mole. So how do we use that information to get us from our empirical formula to our molecular formula?
You would find the molar mass of P2O5 and then divide the mass for the compound by that.
Oh, where's my thumb? There it is. Yes, exactly. So basically, if it was P2O5, what would be the molar mass of that? So we figure it out. So the molar mass of this is the mass of 2 moles of phosphorus. So 2 times phosphorus and 5 times oxygen. And again, we're dealing with atoms here. We're not dealing with molecules. So atoms of phosphorus, atoms of oxygen. So we already figured out that a mole of phosphorus atoms from our previous one is 2 times 30.974 grams per mole. And oxygen is 5 moles times 15.999 grams per mole. So what's our total?
141.943.
139 point.
141.
Oh, 141. Okay.
0.943.
0.94. So 141.94. So if P2O5 has a mass of approximately 142 grams per mole, and our molecule of interest has a molar mass of 284 grams per mole, what's going to be the actual molar mass? Sorry, what's going to be the actual formula? It's going to be 284 grams per mole divided by 142 grams per mole. This is the actual, so you put the actual mass on top and you put the empirical mass on the bottom, and that gives you how much you need to multiply your formula by, and that is 2. So what is our actual molecular formula? What do we do with this number, 2?
So it'll be P4O10.
Exactly. Yeah, it means there's twice as many atoms there as we suspected. The ratio is the same because we've already figured out what the smallest ratio, smallest number ratio, whole number ratio between the two of them. Now we just need to know exactly how many atoms there are. Well, it says there's twice as many. Well, if there's twice as many, we need twice as much phosphorus, and we need twice as much oxygen. So our final answer is P4H10. And then finally, what do we call that? What will we give that? Oh, H. Oh, sorry. O10. What do we call that? P4O10.
Tetraphosphorus deoxide.
There you go. Yeah, excellent. Yeah, it is. This is not, is this an ionic compound or is it a covalent compound?
Ionic.
Is it?
Oh wait, no, covalent.
Right, because they're both non-metals. There's no metal here. They're both non-metals. So those are covalent bonds, not ionic bonds. So if it's a covalent compound, we actually have to say exactly how many atoms are in there, because we know from doing our Lewis structures that non-metallic atoms can form all kinds of crazy combinations. Ionic compounds are much more reasonable. we know what the charge of one is, we know what the charge of the other is. They're always going to balance the same way. But when you have non-metals that can form double bonds and triple bonds and all kinds of weird things, we have to say exactly how many atoms. So we go mono, di, tri, tetra. So 4 for phosphorus, and there's 10 oxygens, and that's deca, like a decathlon. So decoxide, which is that's a mouthful. Okay.
Would they be asking for the name of the empirical formula or the molecular formula?
Only the molecular formula, because we don't care what the name of the empirical formula is, because that doesn't exist. That isn't what the compound is. The compound is actually P4O10. It isn't P2O5. So we don't care what that name is. Okay?
Thank you.
No problem. So the next one's just on average masses. Do we know how to figure out average masses? Fairly straightforward here. We just take the mass. This is the mass of, whoops, let me go back. This is the mass of bromine 79. Now this is where we put the mass of, what are these two? Anyway, what do we call them? We have bromine 79, we have bromine 81. What do we call those two?
Isotopes?
Yeah, those are isotopes of the same element. They're the same element, but they have different masses because they have different numbers of neutrons. So this is the precise atomic mass of bromine 79. And this is the precise atomic mass of bromine 81. Now the problem that students get in with this is that they figure, okay, I'll just add them both together and divide by 2. Well, you could do that if 50% of the bromine was 79 and 50% of it was 81, but it's not. So you have to consider what the abundances of each one are. And this is especially true when you have, like, sometimes some elements have like 5, 6 different isotopes. So you just multiply by the abundance. So there is 50.69%. You divide that by 100 to get an actual number. This one is 4931. Then you add those together and you get the average atomic mass. Just remember that you have to have both the abundance and the precise mass of each isotope. Just remember the abundance part. That part's really important, because some isotopes are so limited in their amount that they don't really change the atomic mass very much.
For that one, once you get those numbers, after you multiply, you would add them together and divide by 2?
No, you just add them together.
Oh, okay.
Yeah, just add them together, because 0.5069 and 0.4931 together add up to 100%. So what you would get is the mass of 100% of both. You just add them together. Don't have to divide by anything. Okay. Oh, now we're dealing with electron configuration. Oh boy, oh boy. So you want to have a quick look at this one?
Yeah.
So what does the noble gas electron configure? What does that mean? Noble gas electron configuration.
Like, instead of writing the entire thing out, you write it out to the nearest noble gas.
Right. We could start with 1s2, 2s2, just keep going and going and going. But with the noble gas shorthand, yeah, we just find whatever noble gas is the next smallest and just start from there. And so this is a great chance to use your periodic table. So what element is mercury? What's the atomic number of mercury.
$80.
I'm looking for it myself. There it is. Yeah, 80. So mercury is 80. So what's the next smallest noble gas?
Xenon?
Xenon, right. So we just put, and xenon is 54. So we've already accounted for 54 to the 80 electrons just by doing this. Just put square brackets around it. So that tells us we have the electrons of xenon, and then we just start adding them on from there. So, and this is where you can use your periodic table. You don't even have to look anything up. You just use the periodic table at this point to fill in the rest. Because we start, xenon is here, right, 54. So then we come all the way across to 55, which is cesium. And we go down how many shells is that? 1, 2, 3, 4, 5, 6. 6 rows down. So that means we're starting with 6. And which block is this at the far left end of the periodic table? Do you remember which block it is? There's S block, P block, D block, and F block.
S.
It's S, right? Because there's 2 of them. 2 electrons. So that's 6s2. And then we just keep going. So cesium, and then so 56, and then 57 is down here, and 57 goes all the way across. So that is which block is this one?
D.
Nope.
F.
That's an F, right? Because there's 14 going across. That is an F. And which one is it? That is 4F, I believe. It's the first F we see. So this is the first block, the first F block. And the very first, when's the very first shell where we start to see F orbitals? If it's the first F block, it's the very first time an F orbital appears. And which shell is that? Is it 1, 2, 3, or 4?
Four.
Yeah, right, because S1 just has S, 2 has S and P, 3 has S, P, and D, and 4 is the first time S, P, D, and F show up. So that's 4F. And then so that takes us to, wait a minute, 54, 80. I'm making a mistake here. Oh no, it's 26, duh. 26 electrons we need to fill in, idiot. All right, so that's a full F shell. So how many electrons in a full F shell?
14.
14, right. So that takes us to 71. So then we come back to 72. So now we're at 72, hafnium. And then we go across till we get to 80. So which shell is this? This one in here. The one, sort of the one in the middle.
D.
That's D, right. So that is a D orbital. That is a D orbital. And it is the third one. It's the third time, it's the third D orbital. So again, 1, 2, 3, 4. First time we see a D orbital is in the third shell, right? Because we have S, P, and D. When is the third time we come across a D orbital? The first time we come across it is in number 3. Where's the third time we come across it?
Number 4.
That's the 4th time we come across it. I'm sorry, that's the 2nd time we come across it. So 4 has S, P, D, and F. So this is the first time we see it. This is the 2nd time we see it. When's the 3rd time we see it?
5D.
5, right. 5. And we need how many more electrons? We have to go from 72 or 71 actually over to 80. So we need 26 more electrons. I have 2 here, I have 14 there. How many more do I need?
10.
10, yeah. So that should be it. Hopefully that's right. So we can actually look that up. Is that the right electron configuration? I may have screwed this one up. Because then the other way you can figure this out is by writing out the little formula for how you fill up the shells. Do you remember how to do that? You go 1, 2, 3, 4, 5, 6, 7, and then across you go S, P, D, and F, and then fill them with the arrows going. Do you remember how to do that? Should we review how to do that one?
Yeah.
All right. So it's 1S, 2S, 2P, 3S. Actually, let me make that a little bit bigger. Okay, so make this bigger. So I go 1, 2, 3, 4, 5, 6. And then across, you go S, P, well, wait a minute, S, P, S, P, D, S, P, D, F, S, P, D, F, S, P, D, F. And then the way that they're filled, the order in which they're filled, we use arrows going down at a diagonal like this. So is this looking a little more familiar? So the order is 1S and then 2S and then 2P and then 3S and then 3. Now I'm getting confused. So it goes 1S, 2S, 2P, 3S. Then we come around again and then we get oh man, I have screwed this up. I apologize. S, P, D. Then like that. 3S. Let's start over. It's important to have a straight edge when you're doing this. So 1, 2, 3, 4, 5, 6. S, S, P, S, P, D, S, P, D, F, S, P, D, F, S, P, D, F. Okay, that's a little straighter than I had it before. So then 1S, 2S, 2p, 3s, 3p, 4s. So let's go 1s, 2s, and then 2p, 3s. And then we come around again, 3p, 4s. Then we come around again, 3d, 3p, whoops, wait a minute, 4p, 5s. Then we come around again, 4d, 5p, 6s. Come around again, 4f, 5d, 6p. So this was where we were. So we started with 6s, and then we filled 4f, and then we filled 4d. So we were right. That's the right order to go in. So this will help with our next question. So did anyone look up the electron configuration? Did we get it right?
Yeah, that's right.
That was right?
Yeah.
Thank God. Okay. Oh, wait a minute. Oh dear, everything left. All right, so we had xenon, and then 6s to 4f, 14, 5d, 10. Okay, so that is the noble gas. So next would be how to draw out the orbital diagram. You remember what the orbital diagram looks like? I sort of made it a little more obvious when I said it's the one with the arrows. The orbital diagram is the one where we draw the actual orbitals out and use arrows to show the electrons. So to do that, we're going to basically skip the first 54 because that would take forever. But we know the order we should fill these in is 6s2, 4f14, 5d10s. So what we're going to do is draw 6s, 4f, and that has 7. So 1, 2, 3, 4, 5, 6. And then 5d10 would be on the top because it's the last one to be filled. Last one is 5d. That has 10. So 1, 2, 3, 4. Okay. So each box, or wait, this made a mistake here. This should only have one box, right? This is an S, there's only room for 2. So each box has room for 2 electrons. And remember, the first one that goes in always points up. And then the second one that goes in always points down. And so these are all going to be filled. This is going to be filled, this is going to be filled, and that's going to be filled. So we can fill in all of these. And then it will only become a thing when we want to say which one is the last electron placed. So let's fill these in the right order. How do we fill these? How do we fill in a d orbital in the correct order? Where does the first one go? First electron.
First one goes in the first square, but then the second one will go in the second square and not.
Always pointing up, right? So first, second, third, fourth, fifth. That's how we fill them in one at a time. And next, we start adding the next group. 6, 7, 8, 9, 10. So it's this one. That's the last electron placed. So the question is, what are the 4 quantum numbers of that electron right there? So where do we start? What are the 4 quantum numbers?
One of them is D, right?
Yep, one of them is the D. One of them describes what the d orbital is. One of them describes that it's fifth. And then there's two other numbers. What's the first one? What's the very first quantum number?
10.
What's the very first one? Just that we want to know. It gives us like the most basic information of where an electron is. What's like the first thing we want to know about where an electron is?
The shell.
Right, exactly. We want to know which shell it's in. So which shell is that electron in?
5.
Mm-hmm, right. So the very first one, N, remember N is the principal. N tells us which shell it's in, and it's in shell number 5. What does the next quantum number tell us?
The D, right?
Right, which is what? What do we call D? D is a
Energy level.
5 is an energy level. It's the next one below that. So if D is a shell, if 5 is a shell, D is a one below a shell, one underneath a shell, a
Subshell.
subshell, exactly. And that is L, right? L, I believe it's the second one. It's been a while. No, L's the third one. No, that's right. L. L tells you which subshell it's in. So which subshell is it? Remember, these are all numbers. We can't give it a letter.
3.
3, right, because we have S, we have P, we have D, and we have F. And that is 1, 2, 3, 4. So L tells us which subshell it's in. It's the third subshell after S and P. It's D. So L is 3. What's the next one? What's the next? So now we have 2 basic bits of information. This tells us that that electron is in 5D. But we still need to know exactly where it is. How do we know exactly where it is in the D subshell?
It's like plus minus 3.
So plus and minus. Where do we use the plus and minus?
Oh, is it plus minus 5?
Mm-mm. So the first one we're looking for the shell. Second one we're looking for the subshell. What's the third place we're looking for? It's in one of these. What do we call these?
The orbital.
The orbital, exactly. So now we need to know which orbital it's in. And that, if you remember, is M to the L, or the magnetic, why it's called the magnetic. I guess it's called the magnetic because if they're all pointing in the same direction, it's a magnetic atom. That makes sense, I guess. So we need to know which, oh, damn it, no, it's not 3, it's 2, I'm sorry. When you have S, P, D, and F, this is 0, 1, 2, and 3. I made a mistake. I apologize. So L is 2. And it'll make sense in a second. So S is 0, P is 1, D is 2, F is 3. See, it's easy for me to make these mistakes. So N tells us which shell it's in, L tells us which subshell it's in, M to the L tells us what orbital it's in. How do we name the orbitals? What description do we give to the orbitals?
-2, -1, 0, +1, +2.
Right. We see what L is. That's why it's M to the L, because we use L to figure out where in the subshell is it. And it starts at -L, which is 2, and it goes to +L, which is +2. And then the ones in between are -1, 0, +1, and +2. And so which orbital is it in?
+2?
It's in +2, right? That tells us it's in the last one, basically. It's the last one to get completely filled, is the +2. And what's the last quantum number we're dealing with? So we know what shell it's in, we know what subshell it's in, we know what orbital it's in. What's the last bit of information we need to know about an electron?
The spin.
The spin, right? That's m to the s. And that tells us whether it's spinning up or whether it's spinning down. And it's spinning down, so what description do we give it? What number do we give it?
-1/2.
That's correct. The first one in is +1/2. Second one in is -1/2. So listen to me. So the four numbers are 5, 2, +2, and -1/2. That gives us the complete information of exactly where that electron is and what spin it's in. So there's basically, that's all the information we need about an electron. All right, man, we got through that one. Okay. So this is just a typical question, figuring out how much atoms go where and to where. So that's our favorite kind of question as chemists. Anyone have trouble with this one? What's something you have to look out for with these? There's a trick that I've played here that's kind of mean. What's something you need to look for? The very first thing when you look at a question like this.
That the equation is balanced.
Exactly. Is it? Is this equation balanced?
No.
No, I deliberately did not balance every equation in this because that's something you need to look for. You need to be on the alert because they're not always going to be balanced. So that's always the first thing you need to look at to see if it's balanced, especially in a stoichiometry question like this. If it's not a balanced equation, you're hosed. So where do we start? What's not balanced here?
Chlorine.
Yeah, chlorine's not balanced, right? Because we have 2 on the reactant side, but we have 4 on the product side. So how are we going to deal with that?
Isn't there actually 6 on the product side?
Oh, you're right.
So then you would put a 3 in
There you go. Yeah, so we need a 3. So 3 would go here. And it's, everything else is balanced. Yeah, 1 mole of carbon, 2 moles of sulfur. Yeah, so now we're good to go. So what will we do next? So we have 25. Which one is carbon disulfide?
The one on the left.
Yeah, the CS2. That's carbon disulfide. So we have 25 grams of that. So how would we solve this one? We don't even have to go all the way through, but if you know how to start, you can finish it.
You convert 25 grams of carbon disulfide to moles.
Yeah, exactly. So carbon disulfide, but how much would so we want moles. We put moles on top. Carbon's got a mass of 12. Sulfur's got a mass of 32. Yep, 32. 32.06 actually. So that is 64 and 12, so it's around 74 grams. So that gives you the number of moles. So 25 divided by 74. So I've got 0.3378 moles. So what do we do?
Then you multiply that by 3.
Right, so basically we just need to convert moles of CS2 to moles of chlorine. So we just multiply this now by 3 moles chlorine, divide it by 1 mole CS2. Always do this because it's real easy when you're in a hurry to say, okay, there's a 3-to-1 ratio to divide by 3 rather than multiply it by 3, because I do that all the time when I'm in a hurry. I make these dumb little mistakes. But if you write out, like I've been, yelling till I'm blue in the face from the start of the class, if you put the units in, you're gold, because if they cancel and you're left with the ones you want, then you're good to go. So, right, so it would be 3,378 moles times 3, so that's around 1. So you would have around 1 mole of Cl2, and then you want to convert back to grams, because the question is how many grams, what mass of chlorine gas. Then you just multiply that by the mass of chlorine. Now, another question, another error that's going to pop up a lot with this, as I mentioned before, we were dealing with atoms of oxygen, right? So we wanted the molar mass of 1 mole of oxygen atoms. Do we have atoms of chlorine here?
They're asking for mass. They're asking for mass in the.
They're asking for the mass of chlorine gas. So here I've got around 1 mole of chlorine gas. What's the mass of chlorine gas?
About 70.9.
Sorry, somebody was sanding some wood or something.
About 70.9.
So how did you get that?
The molar mass, or?
Yeah, the molar mass of chlorine gas.
Yeah, it's just multiply the mass of chlorine by 2, right?
Right. That's the key, because we're not dealing with chlorine atoms here. We're dealing with chlorine molecules. So anytime you're dealing with molecules, you have to figure out, well, how many atoms are in the molecule? 2. So if 1 mole of chlorine is 35, 2 moles of chlorine is 70. So you need 70 grams of Cl2 over 1 mole of Cl2. So always be aware whether you've got moles or atoms, because they're going to be, atoms or molecules, because they're going to have different masses. And so chlorine gas is Cl2, fluorine gas is F2, nitrogen gas is N2, oxygen gas is O2, hydrogen gas is H2. Just, be aware that we're not dealing with atoms, we're dealing with molecules. All right, so here we have a limiting reactant problem. Again, what's the very first thing we need to look for? Another stoichiometry problem. What's the very first thing we need to address?
It's balanced.
Need to see if the equation's balanced, right? Is it?
No.
No, because we have one atom of iron on the left, but we have 2 on the right. So that's not balanced. So how do we balance this one?
Put a 4 in front of the iron, a 3 in
And you
front.
skipped ahead. So 4 here, so 2 here, and then how many oxygens?
3.
3, right. So yeah, without the right molar ratios, you can't answer any questions. So are people comfortable with dealing with limiting reagents? How to figure out which one of these is limiting? How do we figure that out? How would we determine whether iron or oxygen is limiting here?
You would use the molar ratio to find which one produces less moles of iron oxide, right?
Right. We take the total of each reagent and we convert all of it to the product. So I've got 72 grams of iron. I want to convert that to moles. Moles of iron. Iron is, where is iron? Here somewhere. Man, somebody help me find out. Why can't I find iron? Oh, there it is. 55.85 grams per mole. Then we figure out how many moles of product I would get from that. Again, I want moles of product. So I get 2 moles of product for every 4 moles of iron. You can see my moles of iron are crossed out, my grams are crossed out, and the only thing I'm left with is moles of product, which is what I want. So how many moles of product would I get from this? So it's just 72 divided by 55.85 times 2 divided by 4.
.64458.
Sorry, a little louder.
0.64458.
6456. Is that close enough?
644.
Oh, 644. Okay. Moles of iron oxide. Now I do the same thing with my oxygen. So I've got 67 grams of oxygen, not 6.7, of oxygen. Now remember, this isn't oxygen atoms. This, the actual reactant is oxygen molecules, very important. So I have 62 grams of O2. So again, I want 1 mole O2 is like 32 grams. And then I want to figure out moles, again, of product. So I get 2 moles of Fe2O3 for every 3 moles of oxygen. Moles of oxygen are gone, grams are gone, and I'm left with moles of product again. So what's my answer this time?
.396.
1.396?
396.
Okay. So which one is the limiting reactant?
The iron.
The iron, right? Because we get less product when all the iron is used up. So by definition, the limiting reactant is iron. So what mass is produced? Well, all we need to do is to take our 0.6446 moles of iron oxide and just convert moles to grams. So that's pretty easy, right? Just figure out what the molar mass of Fe2O3 is. So that'd be 2 times 55, 85, and 3 times 15.999. That's the molar mass. Multiply it by 6.446 moles, and boom. So you got your, that's how much is made. The tricky part is what mass of the excess reagent remains at the end. So that's actually, it's not that difficult a thing. All you need is this number. So I have, let me just clear that out. To figure this out, all I need is the moles of product. I need the moles of product, and I need how much, and figure out which one is not the limiting reagent. So I know that oxygen is the excess, right? If by definition, if iron is limiting, oxygen has to be in excess. So oxygen is in excess. So the information I have is 0.6446 moles of Ft2O3 were made, right? Because all the iron's gone. When all the iron was used up, that's how much product was made. So this information tells me how much oxygen was used too. It tells me how much iron was consumed. It tells me how much oxygen was consumed. How much oxygen was consumed? Well, what's the ratio between the product and the reactant? I want moles of reactant. So again, I just go backwards this time. Now I want moles of O2. And so it's 3 moles of O2 for every 2 moles of Fe2O3. That tells me how many moles of oxygen were consumed. Not that are left, but were consumed. Because that's how much oxygen it takes to make that much product. So how much oxygen was actually consumed?
Zero point 9669.
9669 moles of O2. That's how much was consumed. What mass of oxygen was consumed? Well, convert moles to grams. That's how many moles of O2 I have. I just multiply that by 32 grams of O2 in 1 mole of O2. Moles of O2 are taken out, and I'm left with grams. So then 32 times 0.9669, I used 30.94 grams of oxygen. How much did we start with? 67. How much did we use? 31. What's the difference? That's the mass of the excess reagent at the end of the reaction. Yeah, so just always use these. These will help you because you could always think when you're doing these sort of questions, what am I trying to get? What answer am I trying to get? And then what information do I have? How do I convert the information I have to the units I want? And by doing these sorts of calculations, you won't get lost. You'll always know what information it is you have. What information do I have? Do I have moles or do I have grams? Do I have moles of reactant or do I have moles of product? If you follow these guidelines, you'll always know which one there is, because the units you're no longer interested in will cancel out and the units that you want will be left over. So that's how you do that one. All right, so this is sort of like the problem we did before, figuring out the empirical formula, with one difference. We're actually burning this compound and converting it into something. So do people remember how to do these? If I can get you started. So remember, so the information we have is that it's composed of carbon, hydrogen, and oxygen, and then we burn it. So when we burn something that contains hydrogen, carbon, and oxygen, what products do we get? So we take this thing, we'll just call it CHO, and when you burn it, what are you combining it with?
O2.
Oxygen, right? And then you're getting products out. What products are you getting out?
CO2 and H2O.
Sorry?
CO2 and H2O.
Right, you get water and carbon dioxide. So you use this information, you get 30.2 grams of CO2, and you get 14.8 grams of oxygen. And you use that to figure out how many moles of carbon and moles of hydrogen you have. So 30.2 grams of CO2, you want moles of CO2. And a mole of CO2 is around 44 grams. So that will give you moles of CO2. It also gives you moles of carbon, right? Because for every mole of CO2, how many moles of carbon do you have?
1.
1. Right, so that tells you how many moles of CO2, and it tells you how many moles of carbon. So that would be 0.686 moles of carbon. Now for water, we have 14.8 grams of water. We want to know how many moles of water we have. Water's 18 grams per mole, left with moles. So that gives us 0.822 moles of water. How many moles of hydrogen do I have?
Zero 0.411.
So you know it's a 2-to-1 ratio, but you did the classic thing. You divide it when you should have multiplied, right? So if you want to know how many moles of hydrogen, you then multiply by 2 moles hydrogen atoms over 1 mole of water. That gets rid of our moles of water and leaves us with moles of hydrogen atoms. So it's actually twice as many. So that gives us 1.64 moles hydrogen. Now, how come we can't use oxygen? How come I just can't say, okay, well, I have 2 moles of oxygen here, and I've got 1 mole of oxygen there, and figure out how many moles of oxygen?
Is it because they both have oxygen?
Yeah, they both have oxygen, but the thing is, I only have 1 source of carbon. It's from the thing I'm burning. I only have 1 source of hydrogen. It's also from the thing I'm burning. Problem is, I have 2 sources of oxygen, right? There's oxygen in the molecule I'm burning, and I'm also burning it in oxygen. So I don't know where the oxygen in these molecules comes from. So most likely it's coming from the oxygen in the atmosphere I'm burning it with, because you usually do this in an atmosphere of pure oxygen under high pressure. So it's probably none of this oxygen generally will be from my molecule. So if it's not from my molecule, I can't consider it. So how am I going to figure out how many moles of oxygen are in my product? So I'll just collapse this down and give you the information we have so far. So this is the only information we have so far. I have 0.686 moles of carbon, and I have 1.64 moles of hydrogen. And I have 12.1 grams of a compound. That's it. That's all I have to figure out how much oxygen I have. How am I going to use that to figure out how much oxygen was present?
Would you divide the moles of hydrogen by the number of moles of hydrogen by the number of moles of carbon?
Okay. But I don't know how many. So that'll give me the ratio of carbon to hydrogen. We know it's going to be like roughly 1 to 2.5. But that doesn't help me with we need to know how many moles of oxygen we have. Because remember, when we get the empirical formula, we always divide by the lowest number of moles. But I don't know how many moles of oxygen I have yet. That might be the smallest number. I don't know. So we'll do that eventually, but we can't do it yet. Right now, I need to answer how many moles of oxygen I have.
Do you find the moles of the compound and subtract?
I don't know what the molar mass of the compound is. Now remember, I have grams of compound, but I have moles of carbon and moles of hydrogen. So what do I do with my moles of carbon and hydrogen? The only information I have about my compound is how much mass there was.
So would you convert the moles of carbon and hydrogen to grams?
That's right. I convert these moles back to mass because the information I have is 12.1 grams is the mass of my carbon plus the mass of my hydrogen plus the mass of the oxygen. The information I have now is moles of carbon and moles of hydrogen. Well, if I convert those two back to mass, then the remainder must be oxygen. So I'll just convert these two to masses. So carbon is 12 grams per mole, and hydrogen is like what, 1.07 grams per mole. And that'll give us grams. So I have 1.66 grams of hydrogen. I have times 12, I've got 8.23 grams of carbon. Now remember, the remainder got to be oxygen. So I just add those two together and subtract from 12.1. So I have 8.23 plus 1.66 minus 12.1. So the remainder of the mass is 2.21 grams of oxygen. Now I need to figure out how many moles of oxygen I have, because then when I have moles of carbon, I have moles of hydrogen, I have moles of oxygen, I can figure out what the ratio is. So this is my grams of oxygen. I want moles of oxygen. Remember, I want moles of oxygen atoms. I don't want moles of oxygen molecules, because it's atoms of oxygen in this molecule. So it's 15.999 grams. Whoops, no, I almost did it. 1 mole of oxygen is 15.999 grams. Cancel out grams. And I've got 0.138 moles of oxygen. So now I got my moles of carbon, I got my moles of hydrogen, got my moles of oxygen. I got everything I need to figure out what's the ratio of them. So how do I figure out what the ratio is?
Divide by the smallest number.
Divide by the smallest number. Divide by the smallest number of moles, which is oxygen, right? So I divide them all by 0.138. So how many moles of carbon does that give me? So oxygen becomes 1. How many moles of carbon?
5.
So C5. How many moles of hydrogen?
11.88.
H11O1. Remember, we don't include the 1.
It says 11.88.
Oh, what is it? 11 point what?
88.
I still can't hear you.
11.88.
Oh, 11.88. Yeah, I would just round that to 12. Just round that to 12. Yeah, so if you have something, when you divide everything and you get something like, let's say 2.33, well, the obvious thing to do to round that up to a number is to multiply it by 3. If you get a number like 5.25, well, the obvious thing to do there is to multiply by 4. Same thing if you get something like 5.67, you multiply that by 3. But if you get something like 5.89 or 5.92 or something like that, then the errors in these calculations are going to be enough that this is close enough to 6. It's when you have something like 5.5, that's going to be multiplied by 2. Or you have 0.25, that's going to be multiplied by 4, or 0.33 or something like that. But when you have something that's really close to 1, like let's say 5.09 or something like that, this one you just round down. This one you could just round up, okay? They have to be really far from 1 in order to multiply it anymore. So like 0.5, that's a long way from 1. 0.25, that's a fairly long way from 1. But if you're within like 0.1 or so, just leave it. Round up or down. All right. So everyone remembers how to do oxidation numbers, hopefully. We need a little review on this one. Why don't we do one of them? Why don't we do S2O3? Is that how to do it? I don't know, it's been a while. I think that's it. Okay. So how will we assign oxidation numbers to these two, to this molecule?
0, not 0. O is -2.
Yeah, all the oxygens, so oxygen is more electronegative than sulfur. And so oxygen is always -2, except when it's down to itself or fluorine. So that's going to be -2, -2, -2. What about the sulfurs?
+2.
That's a little trickier.
Is +2.
Hmm?
+2.
So if we make that one +2 and that one +2, then overall we get to -2. Now remember that sulfur on the left is +3 and the one on the left is +1. For the life of me, I can't remember why. So I'll have to go back and look at that one again. But yeah, that you'd be fine with that one. What about chlorine? What's the oxidation number of chlorine?
0.
0, right? Because it's in its most stable form and it's only bound to itself. So basically, any element in its most stable form, because it has an oxidation number of 0. Chlorine is bound to itself, so it can't take electrons from itself, so it would be 0. Now what about vanadium +3?
+3.
Yeah, just +3. And let's just look quickly at the nitrate ion. So in O. So what are our oxidation numbers going to be here?
-2 and +3.
So who's -2?
Oxygen.
Yeah, oxygen. This is when it's -2. Don't be fooled by the fact that this oxygen has -2 but it's not, it isn't charged. This one is. Its oxidation number is still -2. So what does that leave nitrogen being?
+3.
It's got to be +3, because remember, the three of them have to add up to whatever the charge of the molecule is. Okay. I'm pretty sure you're going to want to look. You're going to want to do this one. I'm assuming everybody wants to do this one, right? Balancing redox reactions. I did this one earlier because I couldn't remember how to do it. So what's the very first thing we need to do with a redox reaction?
Balance everything except the hydrogen and oxygen.
Even before that. So I guess we could do that first. Sure, that makes sense. All right, let's balance everything except oxygen and hydrogen. So what do we need to balance?
Chlorine.
Chlorine. So there's only one on the left side and there's 2 chlorine atoms on the right. So we need a 2 here. Anything else we need to do? Zinc is balanced, right? There's 1 zinc on both sides, and the oxygen and the hydrogen we'll deal with later. So what's the next thing we need to do?
Write the oxidation numbers.
Exactly. We need to figure out who's being oxidized, who's being reduced. Right now, we don't know. So I've got ClO3. What are going to be the oxidation numbers for chlorine and oxygen there? Excuse me. Well, we know what oxygen is, right? What's oxygen always?
-2.
Always -2, right? So if oxygen is -2, what's the oxidation number of chlorine going to be?
+5.
+5, right. What's the oxidation number of zinc here on the left?
0.
That's 0. And hydrogen is what?
+1.
+1. So what's the oxidation number of chlorine on the product side?
0.
It's 0 here. And what's zinc now on the product side?
+2.
+2. And I've got water. So what's the oxidation number of the oxygen? -2 again. What's the oxidation number of the hydrogen?
+1.
+1. So whose oxidation numbers have changed?
The chlorine and the zinc.
Yeah, chlorine is changed from being +5 to being 0, and zinc has gone from being 0 to +2. So who's getting oxidized?
The zinc.
Right. So zinc is being oxidized, and who's being reduced?
The chlorine.
Chlorine's being reduced. So what's the reducing agent?
The zinc.
Zinc.
Zinc, right. And it's almost always a metal when you think, so when you're wondering what's going on, it's almost always a metal. And when you think about it, that makes perfect sense, right? Because what do metals just love to do? Love to give electrons away, right? That's basically their raison d'etre, it's giving away electrons. So almost always, you start out with an uncharged metal on one side, it's going to be an ion on the other side. And metals are always positive ions, so they're always losing electrons. And so basically they get oxidized so that other atoms get reduced. So the reducing agent is zinc. So what's our next phase of attack? What do we need to find out next? Now we figured out who's getting oxidized, who's getting reduced. What do we want to do? We want to break the reaction up, right? What do we break it up into?
The oxidation reaction and the reduction reaction?
Precisely. We need to break it up into a redox reaction. It has two parts, an oxidation and a reduction. What's the reduction reaction?
Two ClO3 minus to Cl2.
Goes to Cl2. Right. So does that involve adding electrons or removing electrons?
Adding electron.
Adding them, right, exactly. So we need to add electrons. How many?
Is 10.
10, that's right, 10, because I've got 2 chlorine atoms. Each of them are +5, and I have to reduce each of them to 0. That takes 10 electrons to do that. And then the other thing that's going on is just that I have H plus and it's going to water. So I can just, that's not really part of what I can put that in there. So what is my what is my oxidation? That's my reduction reaction. What's my oxidation reaction?
Zinc to zinc 2 plus.
Right, so zinc goes to zinc 2 plus. So is that, which side of the reaction are the electrons going to be? Are they products or are they reactants?
Products.
They're products, right? I'm getting electrons out of an oxidation reaction. I'm removing electrons from zinc. How many electrons?
2.
2, right. So there's an obvious problem here. I've got 2 electrons in my oxidation, but I got 10 in my reduction. So how am I going to deal with that?
Times 5 to the bottom equation.
Right. This has to happen 5 times in order to generate enough electrons to carry out my reduction reaction. So I need 5 of these. And then this becomes 10. So now I have balanced my electrons. So the electrons are balanced. What do I need to balance next?
H plus.
Yeah, I basically we need to balance charge, right? We have to have the same amount of charge on each side. So this is where it becomes important to figuring out whether you're an acidic solution or a basic solution. Because you either balance charge by adding protons, if it's acidic, or you add hydroxide ions if it's basic. And in this instance, it's in an acidic solution, so we're gonna add protons. So look at the oxidation. This is our reduction. This is our oxidation. Is our oxidation reaction balanced in terms of charge?
I think it's balanced.
It's what?
I think we don't need to add anything on the oxidation.
Is the charge balanced in the oxidation reaction? Do we have the same charge on each side?
Yes.
Yes, we do, right? There's no charge here. And there's no charge here because I have 10 positive charges and I have 10 negative charges. So they're balanced. But what about the reduction reaction? Is that charge balanced?
No, it doesn't balance.
No, it isn't, because I have no charge on this side. But on the other side, what's the net charge on the reactant side?
12.
12, minus 12, right? Because I have 2 chlorate ions for minus 2. I have another 10 electrons for minus 12. And I have 1 proton. So it's a net minus 11. So that's a big difference. I need to balance out my charges. And the only thing I can do is add protons to one side or the other. So where do I add protons and how many do I add? So here I've got a minus 11 charge, and here I've got no charge. I can only add protons with a plus 1. How many do I add and which side do I put them on?
Add 11 protons on the product side.
Product or reactant side?
Product.
Nope. Product is this side.
Reactant.
Reactant side, yes. I add another 11 protons to this side. And there's already 1 there, so 12. So I have 12 protons. So now I have no charge on either side. But I need to balance my hydrogens and my oxygens. So if I have 12 hydrogens on this side, how am I going to balance that on the other side?
6.
6 waters, right? 6 waters. And if you'll notice, that also balances my oxygens. And that is usually how we balance our oxygens last, and that's usually how we balance them. Once we've balanced the hydrogens, basically the oxygens hopefully take care of themselves in terms of water. And look, we have 6 oxygens here, and we have 3 times 2, 6 oxygens there. So we've balanced everything. Now we add the whole thing together. So let me write the whole thing. So the whole thing is 2 chlorate ions plus 5 zinc plus 12 protons plus 10 electrons make 1 chlorine plus 5 zincs plus 10 electrons plus 6 waters. That's the whole thing. Yep. So we can get rid of our electrons because they're the same on each side, right? So I've got 10 electrons as products. As reactants, I get 10 electrons as products. That's cool. What's the last thing we want to check to make sure that we've done this properly?
Charges on both sides.
Bingo. We have to make sure. So we know that the atoms all balance because we did that already. We balanced them when we balanced the reaction, the oxidation and the reduction. We balanced all the atoms in those. So we know that those are balanced. We balanced the charge on both sides with the electrons. So we did that. But now that we've eliminated the electrons on both sides, we still have to make sure that the total charge of the reactants is the same as the total charge of the products. And if they are, we're good. So what's the total charge of my reactants?
10.
10 what? Plus or minus? 10 plus. So I have 10 plus on this side. And what about the other side?
Also 10 plus.
10 plus, right. The only thing that's charged is zinc, and I got 5 of them for 10 plus. So they balance. So what you want to look for is, in general, not always, but in general, in an acidic environment, your net charge on both sides is going to be positive. And that makes sense, right? Because there's an excess of protons. And in a basic environment, your net charge is more than likely going to be negative on both sides. And that makes sense too, because there's a net increase in negative charge. But they could also be zero. But just don't freak out if you have like a large charge on each side. As long as they're the same, you're good. It's not always going to equal zero. In fact, it rarely does. Usually you have net positive in acidic and net negative in basic. Okay. Great. So are the people fairly familiar with these, hopefully? How to draw Lewis structures and all that good stuff? You want to do one just to get refreshed?
Yeah.
All right. Anyone in particular? Which one?
Which one is the hardest?
I don't know. Just, I don't know, the fourth one maybe? So I underlined which one was the central atom. So that would be, oops. So the nitrogen is our central atom. And so it has an oxygen on this side, oxygen on that side, and a hydrogen attached to the oxygen. So that's going to look like, so what's this going to look like? How many bonds does nitrogen form generally?
Four.
How many valence electrons does nitrogen have?
5.
5. Right, so it normally keeps 2 and makes how many bonds?
3.
3, right. So there's its lone pair, usually has lone pair, unless it's charged. And there's no charge here. Who would it make 1 bond with and who would it make 2 with?
It would make 2 with the oxygen on the right.
That's right. 2 there, 1 there. And it's because oxygen generally makes how many bonds?
4.
How many valence electrons does oxygen have? What
6.
group is it in?
Has 6.
It has 6, right? So remember, when you're making these, you go 1, 2, 3, 4, 5, 6. And you look at that and go, oh, so oxygen has 1 lone pair, 2 lone pairs, and it makes 2 bonds. This is going back a little bit, but yeah, so oxygen makes 2, almost always. Very rarely does it make, well, it makes 1 sometimes if it's charged, but it almost always makes 2. So that gives oxygen each pair. So that would be our Lewis structure.
How did you know that the H wasn't bonded to the nitrogen?
Oh, just the order that it's in. That's why I wrote it like that, HONO, so you'd know what order the atoms were in.
Oh.
Yeah, that's why I just wrote it like that. Yeah, so because otherwise you wouldn't, right? So I wrote it like that deliberately, so you would know which order they would go in. So how many regions of electron density are around the central atom?
2.
How many different places are you going to find electrons around the nitrogen?
3.
3, right. You're going to find some here. Whoops. Undo. You're going to find some here. Ah, yeah,
There's
I keep
4
doing that.
regions of electron density.
I keep finding, why is it doing this? There we go. I'm going to find some here, I'm going to find some here, I'm going to find some here. So 3 regions of electron density. So with 3 regions of electron density, what kind of shape is that going to give you?
Tetrahedral.
That's 4.
Oh, trigonal planar.
Yeah. So the shape, would this be a polar or a non-polar molecule?
Polar.
Yes, it's polar as hell because yeah, you got lone pairs all over the place. It's the shape would be like this, so you'd have the lone pairs and then oxygens. So yeah,
So if something has lone pairs, the dipoles can't cancel out.
yeah, pretty much because yeah, with lone pairs, well, with a single lone pair, yeah, there's no way that those two bonds can be equal and opposite because they're bent like that. They're bent out of shape. And so, and remember that this angle, these are 120 degrees when you have 3 of them. It's going to be a little less than that because you have this lone pair of oxygens or lone pair of electrons pushing these away a little bit. So it'll be a little less than 120 degrees and be polar. Okay.
If something has 2 lone pairs and 2 bonds, can it cancel out?
Generally, no, because that would be in water. Let's look at water. Oops. So water has 1, 2, 3, 4 lone pairs. It has 2 lone pairs and 2 bonds. But so how many regions of electron density are around the oxygen?
4.
4, right. So what shape does that give it?
Tetrahedral.
Tetrahedral, right. So that puts it in the tetrahedral situation. So really, you would have this lone pair and this lone pair, and then this bond and this bond. And remember, the dipoles would be pointing towards oxygen because it's a lot more electronegative than hydrogen. Well, because it's tetrahedral, these angles are around 109.5 degrees, if you remember that. And they're both pointing towards oxygen. So again, they can't cancel out because these 2 lone pairs need to take up space somewhere. And the easiest way, or the best way, to give all these electrons want to repel each other. So the best way to put them the furthest apart is to put them in this tetrahedral shape so that this pair of electrons in this bond and this pair of electrons in this bond and this lone pair and this lone pair are the greatest distance apart they can be. And so that's the tetrahedral shape. And due to the tetrahedral shape, those 2 bonds now are bent. And so this is also polar. Yeah, it's the thing to remember is that these lone pairs take up space. They take up space and they really affect the shape of molecules. We can't just toss them aside. So we have to treat them the same way we would bonding electrons as far as shapes go. Okay?
Thank you.
No problem. So I figured we might want to look at this real quickly. I don't remember if we remember hybridization very well. So people remember how to do hybridization?
No.
I thought not. I didn't remember because it had been a while. So basically what hybridization means is that you want to have the same energy of your bonding orbitals need to have the same energy. So in other words, if I'm making a bond with p orbitals and I'm making a bond with electrons in s orbitals, they're not going to have the same energy, right? They're going to be different because those are 2 different energy electrons. but that's not what we see in molecules. We find that the bonds in a molecule have the same energy. So the only way to explain that is if somehow the s and the p orbitals merged with each other and became equal energy. So let's look at before hybridization. So how many electrons does carbon have?
6.
6, right? So carbon has 6 electrons. How many valence electrons does it have?
4.
4, right? Because it's got 2 are in the 1s, and they're not going anywhere. So we have 4 electrons. So where do we put the first one? So this is 2s and 2p. So where do I put the first electron?
2s.
Mm-hmm. And the second one?
2s.
Yep. And then the next one? So here's my -1, 0, +1 orbitals for my 2p subshell. Where's the first one go?
2p minus 1.
Mm-hmm. And then?
2p0.
Yeah. So the other reason for this, for hybridization, is if you remember, what were the angles between p orbitals? Do you remember? P orbitals look like this, remember? And then there's another one coming out at us and one going back. What were the angles between them?
90.
90, right, because I had one going up and down, one going this way, and then one coming in and out. And they were all 90-degree angles. But, so if we bonded these 2 electrons, we would expect that their bond angles would be 90 degrees, but they're not. So that's the other reason that something's screwy here, something that's not making any sense. So to figure out what's going on, let's actually draw out CO2. So what's CO2 going to look like? So it's got carbon in the middle, and it's got oxygen on this side and oxygen on that side. So what's the total number of electrons that I need to have in CO2?
Wouldn't there be 2 lone pairs for the carbon?
Well, carbon's only got 4 electrons, right? So it wouldn't have 2 lone pairs. Could have 1, because it has a total of 4 electrons.
But what about the octet rule?
What about it?
Is that an exception?
Nope. We haven't finished making this yet. So carbon has 4 electrons, and both oxygens have, valence electrons. Carbon has 4, oxygen has 6, so that's 12. So a total of 16. So we need 16 electrons in here. Right now I've only got 6. So where do the other 10 go?
You have dots around the oxygens.
Okay, so what, put 1, 2, 3, 4, 5, 6, 7, 8. I still got a pair left.
Would you put them in double bonds?
Ah, there you go. Yeah, so if I put them there, then, but now I have double bonds, and these are gone. So then everyone's satisfying our octet rule, right? Because oxygen has 2, 4 lone pairs and 4 electrons shared in a double bond for a total of 8. Carbon's got 4 double bonds, 2 electrons each for a total of 8. And oxygen, the other oxygen is exactly the same. It has 2 lone pairs and 2 bonds for a total of 4, 8. So everyone's got 8, everyone's happy. That's what carbon dioxide looks like. So how many regions of electron density are around carbon?
2.
2. So that's how we figure out what hybridization we need. is how many regions of electron density are there? So there is 2 regions of electron density. So we're going to have to hybridize an S and a P. That tells you what needs to be hybridized. So SP is the hybridization we need. What does that mean? It means that one of the P electrons and one of the S electrons, quiet, hybridize to form SP orbitals. So what does it look like after hybridization? So I'll move this out of the way. So here's my molecule again. So I want to use this to show you something else afterwards. So I'm going to have SP hybridization. So that means I'm going to have two orbitals, one with an electron from an S, one with an electron from a P. So I'm going to have 2 SP orbitals. So my new energy is going to look like this. SP, 2 SPs, and how many electrons do I have left? So those are 2 electrons for my 2 SP orbitals. And how many electrons do I have left for carbon? Remember, I have 4.
You have 2 left?
I have 2 left, right. And where do they go?
In the SP orbitals?
No, I have 2 in the SP orbitals already. Those are going to be my bonding electrons. Those are actually going to be, I'll show you in a second, those are going to be my sigma bonding orbitals. So I have 2 valence electrons left. Where do they go?
In the S orbit? In the S?
My S orbital's gone, right? I took my S orbital and I took one of my P orbitals and I hybridized them. So I have 2 P orbitals left over. Right, because I had 4 orbitals at the beginning, 3, 4, 4. 4 orbitals at the beginning, I got 4 orbitals at the end. So I started with 1 S and 3 P. After hybridization, however, I've hybridized one of the S's and one of the P's. So now I have 2 SPs and 2 P's. You see where the difference is? I've taken one of the S's away and one of the P's away and replaced them with SP orbitals. So I have 2 P orbitals left over that weren't hybridized. And that's where my other 2 electrons go. 1, 2. So that's what the carbon's going to look like after hybridization. And when you look at it, look at the molecule, look at CO2, it makes perfect sense. And I'll show you how. So if you remember, all sigma bonds are made with hybridized orbitals, all of them. All sigma bonds are made with hybridized orbitals. So sigma, how many sigma bonds does carbon make in carbon dioxide?
2.
So it has 2 double bonds, right? Now, in a double bond, the first bond is always sigma or pi.
Sigma?
First one's always sigma, always. The first one is always sigma because if this is going way back, sigma bonds are overlapping orbitals directly between the 2 atoms. So we would have carbon and oxygen, and they have 2 hybrid orbitals that are hybridized so we can have maximum overlap. So that would be our sigma bond. So the first bond of the 2 doubles is sigma. So I have a sigma on this side, I have a sigma on this side. What's the second bond in a double bond?
Pi?
pi. Second one is a pi bond. And the third, if you have a triple bond, the third one is a pi bond as well. And where do so these two electrons, this one and this one, form the two sigma bonds because they're hybridized. They're hybridized to do what? To directly overlap with the oxygen next to it. So that's why they form hybridized orbitals, to get a direct overlap and get very tight bonds. Remember, pi bonds are not as strong because they're from p orbitals. That's where the term pi comes from. They come from pi, from p orbitals. And the p orbitals are at these 90-degree angles. And so I get some hybridization, so I get some overlap above, I get some overlap below. It's not nearly as strong as two electrons that are directly between the two atoms. And so this pi electron, this p electron, and this p electron both form pi bonds. One of them forms this one, that pi bond, and the other one forms this one, that pi bond. Okay? Let's do the oxygen sort of so is this like completely blowing everyone's mind? Is this like something nobody remembers?
Yeah, I don't remember this.
Okay, we'll do the oxygen, and then we'll, well, we got time. We can however many you want to work on. Let's just do the oxygen. Hopefully that'll also clear some things up. So same thing. So I've got CO2 again. All right. So oxygen has 6 valence electrons. So where do I put, so before hybridization, I've got s and p orbitals. Where do I put the 6 electrons?
2s.
Yep, so 2 here. And then where do I put them in the p?
2 on the -1, 1 on the 0, and 1 on the 1.
Right, so I go 1, 2, 3, 4. -1, 0, +1. So there's my 6 electrons for oxygen before hybridization. Well, let's look and see what kind of hybridization we're going to need for this. So now, how many regions of electron density are around this oxygen?
3.
3? 3, right. 3, because I have a region where there's a single and a double bond. So I got one bonding region, and I got 2 lone pair regions for a total of 3. So if I need 3 regions of density, what are my hybridizations? So it was SP when I wanted 2. So now I want 3. So what am I going to have to hybridize this time?
sp2.
That's right. I'm going to need another P. So I need sp2 hybridization. So when I take the S and 2 of the P's, I get 3, 1, 2, 3 sp2 orbitals, and I get 1 P left over. So here's my 1 P left over. So same number of orbitals. I had 4 over here. I got 4 over here. Got 6 electrons over here. I'm going to have 6 electrons over here. So where am I going to put my electrons? So where do I start? Which one's a lower energy, sp2 or P? Remember, you always fill up your lower energy first.
How can you tell which one is the lower energy?
Right, start with the lower energy. So we'll start filling up our sp2. So we'll go 1.
I said, how can you tell which one has the lower energy?
Oh, P, because we've hybridized S and P, so the energy is going to be between S and P. So notice I put it a little bit higher than the S. It's a little bit higher than the S, but not quite as high as the P. So the P is always going to be at a higher energy. So my S is gone. There's no more S anymore. I have sp2s. So my hybridized orbitals are always going to be slightly lower than, they're going to be higher than S, but not as high as P. So they're going to be in between. So our sp2 is a lower energy. So I've got my 6 electrons. So I go 1, 2, 3, 4, 5. But where do I put the 6th one? Think about where the 6th one goes. Does it go in the sp2 or does it go in the P?
SP2.
Okay, so if we put it here, what electrons are going to be doing the bonding? I don't have any unpaired electrons to do bonding. So that would just give me 3 lone pairs.
Oh.
The other thing, so that's one reason why that doesn't work. The other thing to think about is look at what we've done. So we've taken this S and these 2 p orbitals. We haven't done anything to this one, and there's still an electron in it. So basically we've hybridized 3 orbitals, this S and these 2 p's, with 5 electrons. There's 1 left over in the P. And nothing's been done to that. So we had 3 orbitals with 5 electrons in them, and we still do. So before it was hybridized, after it's hybridized, still have the same number of orbitals, still have the same number of electrons, and there's 1 p electron left over. So we haven't done anything with that. So that stays there. And then when you look at this, you realize that makes perfect sense. Why? Because how many sigma bonds does that oxygen make? So both oxygens are the same. So this oxygen here, how many sigma bonds does it make?
1.
1. All right, see you later. Yeah, 1. It makes 1 sigma. And what electron makes that? What always makes sigma bonds?
S.
Hybridized orbitals make sigma bonds. Hybridized orbitals do. So it's this one. Remember, there's no S. S is gone. There is no S. There's only sp2 and p. Those are the only things left. So this single unpaired electron in sp2 forms a sigma bond, because that's what unpaired hybridized electrons do. They form, that's the whole purpose of them, is to form sigma bonds. And just with the carbon, our p electron makes a pi bond. That's the purpose of p electrons. Unhybridized p electrons make pi bonds. So the carbon has an sp hybridization because it has 2 electron regions. Oxygen has 3 electron regions, so it's sp2. It needs 3 hybridized regions to deal with that. And what are these electrons? Where do we find those?
Are those the lone pairs?
Those are the lone pairs, exactly. Those are the lone pairs. So if we were to have methane, so methane looks like this, right? We have carbon and 1, 2, 3, 4 hydrogens around it. How many regions of electron density are around the carbon?
4.
4. So what hybridization will we need for carbon this time?
SP3.
SP3, exactly. We would need SP3. And so, what does that give us? So now we have to hybridize everybody. I've got the S is gone, the 3 P's are gone, and they're completely replaced with 1, 2, 3, 4 SP3 orbitals of all equal energy. Really close to P, but not quite, and much higher than S, but in between them. And we have 1, 2, 3, 4 valence electrons. And in methane, how many sigma bonds does carbon make?
4.
4. They're all sigma bonds because they're single bonds, right? All single bonds are sigma bonds. So it makes 1, 2, 3, 4 sigma bonds. And they're all the same. See, that's the other argument for hybridization, is that without it, carbon has 4 electrons, but they're all different energies. 2 of them are in S and 2 of them are in P. And so, but in methane, it makes 4 bonds and they're all identical. How is that possible? Well, it's possible by hybridization. If we turn them all into hybrid orbitals with all the same energy, then they all form 4 identical bonds, and they have the right 109.5 degree angles between them. So that's the other argument for hybridization. The bond energies are all the same, and it explains why the orientation of the electrons is the way they are. All right, hopefully that wasn't just insanely complicated for everybody. It just sounds like it's just something that we haven't thought about in a while. So it's good to think about these things before the test and not during. All right, so in the time we have left, which ones do people want to focus on? So I realize we've only got like halfway through in 2 hours. So who do we have left anyway? Do we still have plenty of people hanging out? Oh, we got six of you. Okay, which ones would you like to look at? I'm assuming the last 2, the heat questions, but anything else?
Maybe 22.
Okay. 22. Okay, cool. So what this is referring to is if you have 2 substances with drastically different intermolecular forces, they generally don't form solutions, like oil and water have very different intermolecular forces, and so they don't mix. On the other hand, if you have salt and water, they both have highly polar interactions. They mix together, and that works fine. So let's have a look at, let's say A, for instance. So basically, you can just draw them out. Will help. So here's carbon tetrachloride and water. What shape is carbon tetrachloride going to be?
Tetrahedral.
Tetrahedral, right. So this is going to be a completely symmetrical, so we're going to have one going backwards, one going out. So it's going to be completely symmetrical. So is this going to be polar or non-polar?
Non-polar.
It's going to be really non-polar. Because all of its dipoles are going to cancel. And so it's going to have no net dipole whatsoever. So if it has no net dipole, what are the interactions that this molecule is capable of? There's only one.
Dispersion?
Dispersion, that's it. Because there's no net dipole. So the only interactions it can have is sort of like that induced dipole of a dispersion force. So that's it. That is the only one it can do, is dispersion. Now let's look at water. What shape is water?
Bent.
It's also tetrahedral, but it's bent. That's right. It's because it has, we just look at the bonding. We just look at the atoms that are bonded when we look at the shape. So the overall shape of the molecule is tetrahedral, but the molecule of the bonds, and hence the dipoles, is bent. And so the dipoles are pointing like this, right? They're both pointing up towards the oxygen. So this does have a net dipole, right? It looks like this, pointing up towards the oxygen and away from the hydrogen. So what intermolecular forces is it capable of?
Dipole.
It can do dipole. Actually, it can do a special dipole. What's the special dipole it can do? It's even stronger than a dipole interaction.
Hydrogen bonding?
Hydrogen bonding, right. Hydrogen bonding is a subset of dipole interactions that's even stronger. So it does, in a way, it does do dipole, but it does a really strong version of it with a bridging hydrogen. So this is really strong. And as I've mentioned before, it's probably the most important biological intermolecular force is the hydrogen bond. So if I've got one that's only capable of dispersion and one that's capable of hydrogen bonds, are they going to form, will you be able to dissolve one in the other?
No.
No, that's not going to work. So you can't, basically you'll just, whichever one is denser, and I think water's denser, probably. Yeah, they'll just completely separate and one will float on top of the other one. They will not mix. But if you take something like bromine and carbon tetrachloride, let's look at bromine. So we already have carbon tetrachloride over there. Let's look at bromine. So there's a bromine molecule. Does it have a net dipole?
No.
No, it doesn't, right? Because you got bromine on one side, bromine on the other side. They're equal pulling on those bonding electrons. So there's no net dipole. So it's the only force available to it to interact with other bromine molecules?
Dispersion.
Dispersion, exactly. So I have one molecule that's capable of only dispersion. I have another molecule capable of only dispersion. Are they going to mix and together?
Yes.
Yes. Yeah, they will, because they can form dispersion interactions with each other. And the reason why, you might argue, well, water can form dispersion interactions too, and that's true, because every molecule can. The difference is that if water could form, if water could form a dispersion interaction or a hydrogen bond, the hydrogen bond is much more stable. You lose much more energy when you form a hydrogen bond than you do dispersion. And so it's much more stable for water to form hydrogen bonds. It actually has to break a hydrogen bond in order to form a dispersion interaction with carbon tetrachloride. So it's not going to do that. It's going to remain in a hydrogen bonding reaction with itself. That's why when you throw like oil in water, the oil sort of just pools up in the middle and sticks to itself. But when you turn the heat up and it starts to boil, you'll notice that those interactions then start to break up, because now there's sufficient energy to break those hydrogen bonds between the water molecules. And now it's sort of more free to interact with the oil because there's less of an energy difference. But when there's not a lot of heat around, the difference in stability between a dispersion force and a hydrogen bond is huge. When there's a lot of energy around, the difference isn't quite as great. So what you're looking for here are, can two molecules form similar interactions? And if they can, they'll mix together. And if they can't, they won't. So example here would be methanol or ethanol. That's ethanol, and that's water. So ethanol looks like this. And we know what water looks like. So what sort of interactions can methanol make? Is it polar?
Yes.
It is, right? Because this isn't polar, this isn't polar, but this sure is. So we've got a dipole here, a fairly big dipole here. And what other interaction can methanol do?
Hydrogen bonding?
Because it has an oxygen with a hydrogen attached. Doesn't really matter what the rest of the molecule is. We'll just say it's X. But if it has an oxygen with a hydrogen attached, it can hydrogen bond. So this can hydrogen bond. So can water. That's why methanol and water, we say they're miscible. They mix together. They form a solution. You know, beer is a solution of ethanol and water. And they don't separate because they each can hydrogen bond. So if we look here, CH5H12, C6H14, they're both hydrocarbons. Hydrocarbons don't have any net, they're very nonpolar. There's no net bond there, no net dipole. Again, they're only capable of dispersion. They will mix together. And so if you have two things that are completely hydrophobic, they mix together just fine. If you have something that's completely hydrophobic and something polar, they won't mix because the polar thing would rather interact with itself. That's a much more stable interaction. So, and the same with the dispersion force. See, you have 5 carbons all in a row. You have 6 carbons all in a row. That's a pretty big region where you can have dispersion force. That's a strong interaction between them. There's a lot of weak interactions, but there's a lot of them. And so that's becomes a strong interaction. All right, let's look at, we'll do 23 and 24 and call it a day. That sound pretty good?
Yeah.
So with 23, we start, so there's a lot of things going on here. There's also some information here that you don't have that you need to answer the question. One is you need to have hopefully you'll remember this, but the heat capacity of water, liquid, 4.184 joules per gram per degree. The other thing you need that you don't have here is the latent heat of fusion. That is the amount of heat required to freeze or melt something. And so that is, for water, is 334 joules per gram. Those are the 2 bits of information you need to answer this question. So there's 2 things going on here. So you have a soda at 20 degrees. So that's its initial temperature, 20 degrees. You have ice, and its initial temperature is 0. And the question is, when all the ice melts, what's going to be the temperature of the soda and ice mixture? Okay? So what's the first thing we need to think about? Where does the first bit of heat go? So it's going to be heat lost from the soda into the ice, right? So then when the soda loses heat, it's going to cool down. So we know it's going to be colder than 20 because when you put ice in a drink, it gets cold, right? Where does that heat go? What's the first thing we need to consider?
Goes into the ice.
Goes into the ice, exactly. What's the ice going to do?
Melt.
Ice is going to melt, exactly. So that's the very first thing we need to think about is how much energy does it take to melt that ice? And how much energy is that?
334 joules per gram.
Mm-hmm. So the energy to melt the ice, so Q ice, is going to be 334 joules per gram times how many grams?
0.18 grams.
18 grams, right. 1, 2, 3 kilograms. So it's 1,000. So we move 1, 2, 3 orders of 10 over 10, 20, 10, 100, 1,000. It's 18 grams. What's the rest of the heat of ice going to be involved in? So this all occurs, remember, this all occurs at 0. So the ice is going to stay at 0 degrees till it's all gone and it turns into water. That's why there's no delta T here, because ice melts at 0 degrees. And then once the ice is melted, it's not ice anymore. Now it's going to start warming up from 0. So how do we figure out how much heat is going to go into the cold water to whatever temperature it becomes?
So would you? Oh.
Go ahead.
Would you multiply 334 by 18, and then that's the Q of the ice, and then that's the negative Q of the water? I mean, the soda.
That's one. See, there's two things. There's two places where the heat from the soda is going to be lost to. One is melting the ice. 1. 2 is heating that ice water to the final temperature. So that's the two things that the heat from the soda is going to be lost to. So we need to account, we've accounted for 1, we've accounted for the melting of the ice, but now we have to account for taking the liquid water that was ice, that was at 0 degrees, and now it's going to be raised to whatever the final temperature is. So we have to add that to Q ice. Because now we have, the ice is gone, but now we have ice water, which is at 0. So how do we figure out Q for the ice water? Remember, Q equals mass times heat capacity times delta T, right? So our mass is 18 grams. What's our heat capacity?
4.184.
But that's for liquid water. We got ice, don't we? We don't. We have liquid water now. You were right. We don't have ice anymore. Once the heat goes into the solid ice, it's no longer ice. It's now liquid. And so its heat capacity is now the same as liquid water. So you're right, 4.184 joules per gram per Kelvin. Now this is the tricky part. What is delta T?
Is it 20 degrees?
But that's the thing. We don't, the ice water doesn't get to 20 degrees because it's going to be cold. We don't know what temperature it gets to. We know what temperature it started at, but we don't know what the final temperature is. That's the question. So the change in temperature is going to be whatever the final temperature is minus 0. Because we don't know what that delta T is. We know it's positive. It goes from 0 to some temperature, but we don't know what it is. Now, that is the Q of the ice. What is that going to be equal and opposite to?
The Q of the soda.
That's right, exactly. So Q ice is going to be equal to minus Q soda. And Q, whoops, pick a different color. So Q soda is what? Remember, Q is mass times heat capacity times delta T.
So 250 grams times 4.184 times TF minus 20.
Exactly, very good. Yeah, because now the Q of the soda is negative, right? Because it gets cold, so it loses heat. So it goes from 20 down. So its delta T is going to be negative. Whereas the delta T of the ice water is going to be positive because it goes from 0 up. So now we have all the information we need. And now it's just a matter of doing some insane calculations. Basically, we just multiply everything that's together, and we want to get everything with temperature final on one side and numbers on the other side. So we'll just multiply everything out. So this gives us 6,012 joules. So that's what that one is. Plus this times this is, what was it? Oh, 7531 times T final minus 0. And then the other side of the equation is I got a dog desperately jumping, wants to jump on my lap here. Just give me a minute. So the other side is going to be 1,046 temperature final minus 20. Right? So this 10,046 times temperature final minus 20. And then we just solve for temperature final. Remember, one of these is going to be negative. So that's going to be negative. So I put it all together. We end up with 1,100. Oh, I might as well take it through the whole thing. 7531 temperature finals plus 6,012 joules equals minus 10,000 temperature finals minus 20,920. So then you put it all together and you get minus 1121.3 temperature finals equals minus 149.08. Temperature final equals 13.3 degrees. So yeah, it's just get it to this point and then it's just algebra at that point. And you should get, yeah, 13.3. And that makes sense, right? Because you put ice into water, it should decrease the temperature of the water. It's going to be less than 20. Just a matter of always remembering Q of whatever's losing heat has to equal Q of whatever it is that's gaining heat. And remember where the heat goes. The heat goes into two places in this, and that's key to the whole thing. It goes into two places. It goes into melting the ice, then it goes into increasing the temperature of the ice water once it's turned into water. So, last one. This was an evil question I put on a test years ago. It was a bonus question because it was kind of evil.
Do you know how many problems there are on the test?
No, I've not read it. I've not seen it yet, so I don't know. That's something to ask Dr. Sanders. Let's just do this one and get the hell out of here. And remember, if anybody wants like more review, just let me know. We can do this anytime you like, before the exam, of course. So I have a kilogram of dry ice at minus 100 degrees, and then I want to turn it into a gas at plus 100 degrees. First question is, what's dry ice?
A solid.
It's a solid. Solid what?
Water.
That's the whole trick to the question. It says dry ice, not ice. Dry ice is CO2. That's one of the evil parts of the question. It's CO2, CO2 solid. You must have seen dry ice before, right?
Not in person.
Oh, really? Oh, yeah. I guess not everyone's worked in a lab. Yeah, it's one of the, when you work in a biology lab, it's all over the place. You use it to freeze samples very quickly. Generally, when you want things to, when you have like a protein sample or a cell sample or whatever it is, you want to freeze it really, really fast so it doesn't, so all the enzymes don't die in it and everything. So you either put it in some dry ice or you put it in some liquid nitrogen. Either one, they'll freeze like practically almost instantly. So basically all we're doing is taking dry ice at minus 100 and we're turning it into what?
Gas.
Gas at plus 100. So all of this stuff about water is, we don't need any of it because water's not involved in this reaction. So anything that has water in it, you can ignore. That was the other evil part. So I had like, I don't know, 60 people in the class. I think 5 of them got this one right. That's why it was a bonus and not that evil. So does dry ice, does it go from a solid to a liquid to a gas?
No.
It doesn't, right? It goes right from a solid to a gas. So what do we call that when something goes directly from a solid to a gas?
Sublimation.
Sublimation, right. So we don't have a heat of fusion and we don't have a heat of vaporization. We have a heat of sublimation. That's the amount of heat required to take a mole of CO2 directly from a solid to a gas. And at what point does that happen? What temperature does that occur?
Negative 78 degrees.
Mm-hmm. It happens at minus 78. So the way I see it, there's 3 things we need to do. What's the very first thing we need to do? So I have CO2 solid at minus 100. What's the first thing I need to do?
Calculate the change in temperature.
To what temperature though?
The change from negative 100 to negative 78.
Exactly. Yeah, I need to warm that solid piece of CO2 up to its melting point or its sublimation point, because it's not going to sublime until I get it to that point. So that's the first thing we need to do, is heat CO2 solid. What's the next thing we need to do then? Easy, you're stomping on my keyboard. What's the next thing? Now that we have, yes, I know you want to go for walkies. So now that we have solid CO2 at minus 78, what do we do next?
Calculate the heat from that reaction.
Which reaction?
Dry ice to the sublimation point.
But we've done that, right? We've calculated, well, we will calculate how much heat it takes to warm the solid CO2 from minus 100 to minus 78. Once it's at minus 78, what are we doing to it? What happens at minus 78?
Sublimation.
Right, so we need to sublime all of that CO2 to gas. That takes heat, right? So we've got solid CO2 at minus 78, and we need to convert all of it to gas, also at minus 78. So now I have gas at minus 78. What's the third thing I need to do?
Heat the gas up to 100.
Bingo. So now I need to heat my CO2 gas from minus 78 to plus 100. So that's the 3 steps I need to do. So basically all you need to do is for the first one, get a different color here. It's making it hard to write, you know. So for the first one, Q is mass times the heat capacity of CO2 solid times change in temperature, which is minus 100 to minus 78, so plus 22. The next thing is you have CO2 solid at minus 78. So now Q is going to be equal to the mass of CO2 solid times the heat of sublimation of CO2. So you need to, oh, oh, that's lovely. Oh, it's a lovely thing about dogs. They throw up a lot. Yeah, they do. Okay, so the tricky part of this is there's no change in temperature, right? Because it goes from, oh God, because it stays at minus 78 the whole time. But you do need to change this mass to moles. Why? Because the heat of sublimation is given in moles. So you need to turn 1,000 grams of CO2 into moles of CO2. And that's easy enough to do, right? You just multiply by 1 over 44 grams per mole. And then the final one, the third Q, is mass again, this time of gas, because now we've got gas. And again, 1,000 grams, times the heat capacity of CO2 gas. Now that's going to be different. You see the heat capacity of the solid is this. The heat capacity of the gas is less because the gas doesn't increase in temperature as much when you add heat as the solid does. And then you multiply that by the change in temperature. And the change in temperature this time is going to be 178 degrees because you've gone from minus 78 up to plus 100. And then you just add the 3 of them together. Okay? Does that seem to make sense?
Could you go over what the second one says after mass?
Oh, second one. So that heat is anytime you're calculating heat, right? It's heat capacity times mass times the change in temperature, unless you're changing phase. And you're changing phase here. So that's, you need the heat of fusion or the heat of sublimation or the heat of vaporization, whatever change in phase is going on. So in this instance, the change in phase is sublimation. And so the heat involved to do that would be the heat of sublimation, so delta H sub, which is 21.6 kilojoules per mole times moles of CO2. It depends what units you're given. Generally, heats of vaporization and sublimation and all that can, because they have the delta H there, they're usually given like per mole. Because whenever we see delta H, it generally means heat per mole. Sometimes it's given in per gram or per kilogram, but in this instance, it's per mole. So you just need to convert the mass of your dry ice to moles. Okay?
Yeah.
All right. Yeah, so go ahead and run that out. If you have any questions about it, just let me know. We'll go over the calculations. I think what's my final answer? Yeah, I did it somewhere. I'll have to look for it. I'm sure I did that one. Well, I'll have to review it. I think I did. I'm pretty sure I did that one. I just can't find the answer to it right now. All right, any other questions? I gotta clean up some dog vomit. I live such a glamorous life.
Just like a quick question.
Sure.
I'm gonna be returning my lab kit today, so and I have the chemicals in just like this Ziploc bag, and this is basically all I just give them, right?
Yep. Yep.
Okay.
Bag with the, I think there's what, 8 reagents in there?
Yeah, like 8, yeah.
Yeah, and then you're done. Then you
Okay, man.
keep everything else or do whatever you want with it.
Okay, thank you. And also, what's the equation?
Bad stuff with it or whatever.
Also, what's for the first equation for number 1? What does that say? Like,
Oh, this
like,
one?
yeah, it's like heat equals mass times
Heat
something.
capacity of CO2 solid. Because the first thing we need to do is heat CO2 solid from minus 100 to minus 78. So in order to calculate that amount of heat, it's the mass of the dry ice times the heat capacity of dry ice. And that means heat capacity of CO2 solid times 22 degrees, because we're raising it from 100 to minus 100 to minus 78. So that's going to be positive Q.
Okay, thank you.
Yeah. So they're all positive Qs. It takes heat to raise the temperature. It takes heat to sublime the solid to a gas, and it takes heat to raise the temperature of the gas. So they're all going to be positive. So when you add them all together, it's going to be quite a lot of heat. All right. Anything else before we call it a day? And remember, yeah, I mean that. Just send me a message if you want to do a little more of this. If you want to review any of the other questions, or really any question you have, up to any time, since we don't have any labs or anything. So basically, any time between now and the exam. All right. I'll make myself available. All right. Thanks, everybody. Good luck.
Thank you.
Thank you.
Good luck. You're going to crush it. I know it.